So let's consider a couple of different groups. So the first group, let's consider, call it G1. We'll make this plus or minus 1 plus or minus I, viewed as a subgroup of C star, which is notation for the non-zero complex numbers equipped with multiplication as the group operation. So it's just a very simple thing. This is just the powers of I, square root of negative 1, k running through k, 0 through 3. Another group we'll consider is the cyclic subgroup of S4, symmetric group on 4 letters, generated by something I'll call rho. And, well, here's a way of describing what it does. It sort of cycles the things around. It cycles them. So 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1. In a shorthand, we'll be introducing eventually. This might be written 1, 2, 3, 4. Now, you don't have to worry about that, but it's an easy way of just sort of coding what this permutation is. And it's not hard to see that, for instance, well, rho squared is certainly not either the identity or rho. You can see that because if you evaluate rho composed with itself, well, 1 will go to 2, 2 will go to 3. So rho squared takes 1 to 3. And certainly neither the identity nor rho do that. Likewise, rho cubed is not one of E rho squared by the same sort of argument, or just using what we've established already in inverting. I mean, if rho cubed equaled rho squared, then, for instance, rho would equal E, which isn't true. But because these things are just being cycled around, it's not hard to see that 1 will end up back at 1 after composing this permutation with itself 4 times, and likewise for 2, 3, and 4. So this is just the identity. So put another way, the multiplication table for this thing, E rho squared, rho cubed, just looks like E rho squared, rho cubed, then shift this rho squared, rho cubed, E, rho squared, rho cubed, E, rho cubed, E, rho squared. And that follows immediately from this. But that's exactly the same thing as the multiplication table for I. So in some sense, these are really the same group. They just have the same multiplication table, but they're relabelings of each other. Is that fairly clear, or does anybody not see that?
I have to admit I don't see it right.
Okay, sure. So I has the property that its 4th power is 1. But all of the powers in between that and this 4th power are not any of the previous things. So for instance, I squared is not, it's minus 1. It's not the same thing as 1 or I cubed is minus I. That's not 1 minus 1 or I. And so, again, by the same sort of thing, when you multiply the things around, it just sort of circulates them. So call this thing G2. The idea is that G1 and G2 have the same multiplication table. But with a relabeling. So this idea of relabeling multiplication tables gets formalized in algebra under the name isomorphism. So I'll write down a definition now. isomorphism. An isomorphism is a map between two groups, which is bijective, and such that it preserves the multiplication operation. So f of x times y is f of x times f of y, where, of course, over here, this is the multiplication in G1, and this is the multiplication in G2. So this is the same sort of idea. You're just, f is what's telling you how to relabel the things. And the idea that the multiplication table is preserved is just saying that f of x times y is the same thing as f of x times f of y. So here's another example. So in this case, the isomorphism is given explicitly by sending powers of I, so say I to the kth power. So explicitly, in our case, I send the kth power of I to the kth power of rho. So 1 gets sent to the identity, I gets sent to rho, I squared gets sent to rho squared, I cubed gets sent to rho cubed. Yeah, so f of I to the k equals rho to the k. Gives us an isomorphism.